Hello everyone and welcome to lesson 3.2 of engineering geology. Today's topic is crystallography and optical properties of minerals. As usual, we are going to begin with a discussion of the previous lesson's question set. The first question that I asked last time around when we met was I asked for an explanation of the differences between amorphous and crystalline solids. Now, amorphous solids do not show any regular pattern of individual atoms that constitute the solid. On the other hand, crystalline solids have got a regular pattern of atomic structure, regular and repetitive pattern of atomic structure, and this is the main difference. This is the difference actually. This is the essential difference between amorphous and crystalline solids. Now, rock forming minerals are in a sense crystalline solids. Okay, the second question that I asked was explanation of a few terms, the first one being iridescent mineral. Now, what is meant by iridescent mineral is that in minerals, oftentimes what happens, there are inclusions of refractive inclusions that have got different refractive index compared to the host material. As a result, what happens, there is a color. The material actually shows rainbow-like color appearance, a play of color really, because of that difference in optical property. Now, in contrast, we also talked about in the previous lesson, we also talked about basically brilliance or play of color, and we also talked about a thing in which the color of a material changes, of a mineral changes. So, these two things are also because of interplay of refractive index within the different parts of the body of the mineral really, but the type of the characteristic, the optical behavior is different in those two cases. For instance, in case of a situation where play of color is involved, like for instance diamond, the mineral diamond, in which you can see a play of color, that one comes because of diffraction from within the crystal lattice, whereas the other behavior in which a mineral changes color, that is also called by the name labradorescence, because labradorite is the mineral that actually exhibits that kind of property. That one is because of the optical behavior of a particular plane within different parts of the crystal structure, that is called the twinning plane. So, that is basically the difference between play of color, brilliance and iridescence. Now, the second part of this second question asked for an explanation of dull luster. Dull luster essentially is a non-metallic luster which gives a dull appearance, as the name suggests, of the mineral. Now, a good example of dull luster is the luster of a chalk, for instance. Then I asked, as a part of this this question itself, an explanation of Mohs scale of hardness. Now, it is a comparative scale really that distinguishes hardness, surface hardness of different types of minerals. Now, I discussed this thing in detail in the last lesson, but just to recapitulate, what I said is that the mineral talc is basically the softest one, and then we have got gypsum, then we have got calcite, then we have got fluorite, and next comes apatite, next comes orthoclase, then comes quartz, next is topaz, then comes corundum, and then comes diamond. So what it is actually is a 10-point scale in which talc has got a value of 1 and diamond has got a value of 10. So if there is a material, for how to use this scale is like this: if there is a material which has got which scratches gypsum but it doesn't scratch talc, then that particular actually it scratches gypsum but it doesn't scratch calcite, then that particular material has got a hardness in between 2 and 3. So that basically actually is the use of this particular scale, and it gives you in relative terms what is the surface hardness of a particular type of mineral. Okay, reverting back to the question set, the next question that I asked was how hardness for a given mineral may change because of weathering. Now hardness in terms of mho is actually a characteristic of a mineral. Now if because of weathering a mineral changes its chemical characteristic, or it changes from being one mineral to another mineral because of the weathering effect, then for obvious reason hardness will also change as a result. What normally happens is because of weathering, hardness actually most of the time decreases with time. That is not true always, but it is a in general that's what happens. Now the other question that I asked, the last one, was whether you would expect streak and color of a mineral to be identical. Now streak and color are two different characteristics, as I explained in the last lesson. Now streak is the color of a powdered mineral, whereas color is the color is that of the intact mineral. Now these two things are distinct mineral property. I indicated this one in the last presentation itself, that for instance you consider the material, the mineral chromite, and let's examine the color of the streak and color of the mineral itself. The streak of chromite is brown, whereas the mineral itself is black in color. Consider another mineral, magnetite. For magnetite, both streak and color are black. This actually, by the way, streak, magnetite and chromite, they are actually very similar in in many different ways. The only way to distinguish these two minerals, or one of the very few ways in which these two minerals can be distinguished easily from each other, is by looking at the color of the streak. Okay, so streak of magnetite and chromite are different, although both the minerals are black in color. So that kind of gives you an example that streak and color are two distinct mineralogical properties. Okay. Now with that said, let us get back to the core topic of this presentation. Now what are the objectives of this particular lesson? In this particular lesson, we will be able to try to understand what are the different types of crystals, symmetry issues of crystals, and crystallographic axes. We are going to be able to describe optical behavior of minerals and distinguish one mineral from the other by looking at the different optical behaviors. Then thirdly, we would like to identify the crystal structures and optical behavior of a few common minerals. Fourthly, we are going to look at the procedure, essentials of the procedure of X-ray diffraction technique, which is used to identify or distinguish one mineral from the other. And again, finally, we are going to look at a few examples by which XRD can be used, or X-ray diffraction can be used to find out, to identify different minerals. Okay, so these are the topics that we are going to cover in this presentation. The first one we wanted to look at is what we mean by symmetry. Now symmetry is essentially means that if for example there could be planes of symmetry or there are axes of symmetry. Now what is meant by plane of symmetry is that the two parts of a particular body that are on either side of that plane of symmetry, they are identical to each other. Now that is called the plane of symmetry. Now axis of symmetry, how do you define it, is that if you rotate the body about the axis of symmetry, patterns or identical physical appearance, they are going to repeat as the body rotates about that particular axis. Now that repetition could be it generally occurs at discrete angles of rotation, and in that way there could be several different ways of classifying symmetry. For example, we can have binary symmetry, trigonal symmetry, tetragonal symmetry, hexagonal symmetry, and what it means by that is that in case of binary symmetry, if we rotate the mineral about the axis of symmetry, then an identical physical appearance is going to repeat after the mineral rotates by 180 degree. In case of tetragonal symmetry, on the other hand, identical pattern is going to repeat after every 90 degree rotation of the mineral, whereas hexagonal symmetry involves repetition of the pattern after every 60 degree rotation. So you can see that in case of hexagonal symmetry, there is a six-fold similarity if you consider a particular cross section. We are going to look at the details of these categories when we as we progress with the presentation of this lesson. Now there could be also a center of symmetry. What it means by a center of symmetry is that if you look at two opposite faces across the center of symmetry, they are going to be identical. They are going to be having an identical appearance in terms of their orientation and geometry. Now you should also try to notice that a mineral can have several different axes of symmetry while it may have no plane of symmetry, or it may have no center of symmetry. And similarly, it could have planes of symmetry, several planes of symmetry, but there could be situations where there is no axis of symmetry or center of symmetry. We will see these things as we proceed with the lesson of this as we proceed with this presentation. Now, crystallographic axis, what is meant by that? I explained this this term in the previous slide. What it means, what is crystallographic axis in essence is, it gives you a reference to describe the geometry of a particular crystal. More often than not, these reference axes are the axis of symmetry. That is not to say that always crystallographic axes will be identical to axis of symmetry. Now, crystallographic axis could be orthogonal or skew. They do not have to be at 90 degrees to each other, they can be at some other angle than 90 degree, and there could be 3, 4 or 6 concurrent straight lines that form a set of crystallographic axes. All right. Now, let us look at the most simple crystallographic structure. The simplest crystallographic structure is called isometric structure. Now, as the name suggests, the set of crystallographic axes, in this case they are all going to be equal to each other and they are going to be orthogonal. So, this crystal will have similar appearance when you look at the crystal from all different sides. Now, symmetry of isometric crystals, it should have 4 3-fold axes of symmetry and 3 2-fold axes of symmetry. This is the minimum requirement for a crystal to be classified as of the isometric family. So, it should have 4 3-fold symmetry and 3 2-fold symmetry. It should also have a center of symmetry. Now, this thing, for explaining this aspect, I just considered a simple crystal shown on the right side of this slide. Now, this is actually in the form, you can easily see that the crystal is of the cubical form, and actually halite crystals, halite is essentially rock salt, halite crystal is of this type of appearance. It has got a cubic appearance. Now, for this type of crystal, this is the simplest structure really. In this case, you have got you got to have 4 3-fold symmetric axes. Now, those axes are the solid diagonals of this particular form. So, what we have here, the 3-fold symmetries are essentially this one is, we have got AD, this is one of the solid diagonal, then we have got BE, another solid diagonal, and also the third solid diagonal we are going to have is CF. So, these 3 solid diagonals will form actually there will be another one, sorry, there will be another one, and that is going to be HG. Okay. So basically we have got one here, we have got one here, and we have got one here, and fourth one is between H and G. So these are the 4 solid diagonals that are going to cut at a point within the body of the crystal, and that is going to give you also the center of symmetry. Now we are going to show, we are going to show how these solid diagonals are going to give you threefold symmetry. In addition to these things, we are going to have 3 two-fold symmetries, which are going to be, you can consider those axes as the straight lines that pass through the center of the faces, for faces like A, F, E and H. Okay, let me erase the drawing that I did to make it a little bit clear. So threefold symmetries in these cases are going to be along the centers of faces A, H, F, E. So there will be one line that is going to connect the center of A, H, F, E and the center of the opposite face, which is B, G, D, C, and similarly we are going to have another one from here, and we are going to have a third one that is going to connect the centers of H, E, D, C and A, B, G, F. So these three axes are going to be two-fold symmetric axes. Now let us look at the solid diagonals of this particular type of crystal to understand what we mean by what we mean by there being a threefold symmetric axis. All right. Let us consider holding a particular cubic structure on the across one of the solid diagonals. So what we are going to see in this case, what we are going to see at the top are 3 faces, and let us give different color to these 3 faces. So in this case our axis is going to be coming out of that point, out of the tablet here, and what we are going to see when we look down from the top along the axis, we are going to see, as I mentioned, 3 faces. One of them is a red face, the other one is going to be a green face, and the third face that we are going to look at in this case is going to be a cyan face. So these 3 faces we are going to have a look, we are going to be able to see when we look top down through the in the direction of the solid diagonal. Now you can see easily that if you give a 120-degree turn, to this crystal that way, counterclockwise, then what we are going to end up with is that the green face is going to be taking position of where the red face was earlier, and the red face is going to occupy the position which was earlier occupied by the cyan face, and cyan face is going to occupy the space which was occupied by the green face before the rotation. So since these 3 faces are going to be identical, or in other words, what is going to happen, actually let me draw this thing to make it a little bit clear. If you give 120-degree rotation, then you are going to have a situation like this. and this one here is our earlier green phase, and the cyan phase has gone here, and the phase that was red is here. Okay. So, this is actually a transformation that you get after a 120 degree rotation. Okay. So, then again if you apply another 120 degree rotation, then you can imagine what is going to happen. The red phase is going to come back to where now cyan phase is, and so on and so forth. So, what that tells you? This tells us this, that since all the phases are in a sense identical to each other, we are actually getting the same pattern from rotation of 120 degree about the solid diagonal that is at this location. So, we are going to get in that case 3 different configurations for a complete revolution of 360 degrees, which are going to be of identical appearance. So, this is what is meant by a threefold symmetry. Okay. What are the form of this family of crystal system, this family of crystals is called a closed form. Closed form means what we mean by closed form is going to become more apparent as we continue with this presentation. As we continue with this presentation. Now, what are the examples of this class of minerals? You have got the example of halite I have already talked about. Diamond also is of this category of minerals, and then you have got pyrite and galena. If you recall, pyrite is actually ferrous sulfate, and pyrite is ferrous sulfate, and galena is lead sulfate. Okay. Now, these are the examples that we talked about. Pyrite is on the left of this particular slide, and this type of mineral is, as I mentioned, is of isometric class, and the subcategory within the isometric class is diploidal. Now, pyrite has got 2, 3 and 4-fold symmetries. The number of 2-fold symmetries is 3, number of 3-fold symmetries is 4, and number of 4-fold symmetry in this case is 0. It has got 3 planes of symmetry, and as I mentioned before, it has got a center of symmetry as well. Now, you can see here that it meets the minimum requirement of this type of crystal being minimum requirement of that of an isometric form. So, that is the reason this particular type of crystal can be classified as of the isometric family. Now, galena and diamond, they are on the other hand of hexoctahedral subcategory of the isometric type of crystal, and they have got 6 2-fold symmetry, 4 3-fold symmetry, and 3 4-fold symmetry, and these 2 types of minerals have got 9 planes of symmetry, and they, as you can see, these minerals also meet the minimum requirement for being classified in the isometric family. Okay. Now, the second type of crystal system that we are going to consider here. Actually, you can see that we are going to increase the complexity as we go down the line. So, the second type of crystal system that we are going to get is called tetragonal family of crystals. Now, these crystals, what are the requirement for this type of crystals? For them, you have got one axis longer than the other ones. All the axes are orthogonal to each other. So, this is the requirement for a crystal to be classified to be of the tetragonal family. Symmetry requirement here is not very obvious, and that will vary as from subcategory to subcategory of the tetragonal system. The form of this family could be closed or open, and we are going to actually, this is going to be the place where I am going to explain what is meant by a closed form and an open form. And examples of this class of crystals is zircon and chalcopyrite. Right. Okay. So, as I mentioned, the tetragonal symmetry, you have two of the very prominent type of minerals that appear that are of tetragonal symmetry are zircon and chalcopyrite, and these are the examples. Now, both of these type of minerals are of the closed form. Now, give you an example of an open form. Let me draw something here. Say instead of a crystal of this shape, the shape of zircon, if we were to get a crystal which is identical, more or less identical, but of slightly different type, then this type of crystal would be called an open form. You can see that the two pyramids that appear at the ends of zircon actually closes the form, whereas on the one that I have drawn here, let me label it as an open crystal. Here you do not have a pyramid at the bottom of the crystal. So, this essentially is an open form. Now, open form, if you can imagine that if there is a crystal which looks like a simple column, flat ended column, that would be an open form. Or if the column actually closes in one of the ends, that is also an open form, whereas if both the ends are closed, then it is a closed form. On the right hand side, actually you have got a crystal of a chalcopyrite. Here you have got each of the faces gets closes the volume, actually encloses the volume. So, this one also is of the open form, closed form. Let me get rid of this. Okay. Now, let us consider the subcategory. These both these minerals, I said zircon and chalcopyrite, they are of the tetragonal family, but they are of different subcategory. Now, zircon belongs to ditetrahedral dipyramidal subcategory, whereas chalcopyrite it is of the scalenohedral subcategory. Now, zircon has got 4 two-fold symmetry and 1 four-fold symmetry. It has got 5 planes of symmetry. On the other hand, chalcopyrite has got 3 two-fold symmetries and 2 planes of symmetry. Both of them actually meet the requirement of their being categorized as tetragonal crystal, is because you can see that the crystallographic axis in all the cases they are oriented to each other at 90 degrees. At 90 degrees, the angle, the inclusive angle between them are 90 degrees. Let me draw that also. For example, in case of zircon, you are going to have one axis in that orientation, you are going to have another one this orientation, and obviously you are going to have one axis in this direction, and there are going to be the angles between these axes, all of them are 90 degree. Now it is also obvious that the axes towards from top to bottom are longer than the other two axes in this case. So you can see why zircon gets categorized as a tetragonal a tetragonal crystal. All right. Getting back to the crystal systems, the next one in the order of added complexity is orthorhombic. So you can see the first one that we discussed was isometric. We had three crystallographic axes, all of them were at 90 degrees to each other, and all of them were equal. Then we considered the tetragonal family, where we had orthogonal set of crystallographic axes, but in this case we had the angles in between them, in other words the angles in between them were 90 degree as well, but one of the axes was longer than the other axis. In case of orthorhombic, what we got is all the axes are unequal, although all of them are orthogonal to each other. That means here we are going to have again all the axes are at 90 degrees to each other, but all the axes are unequal. Symmetry requirement: the crystals should have at least one two-fold symmetry. The form of this crystal system could be open or closed. In contrast to the isometric system, you could only have a closed form in that case, but here you could either have open or closed. It is quite the same way as a tetragonal crystal family. What are the examples? One of the very common mineral that appears in this family is barite, and you have got a picture, you have got a schematic of a barite crystal on the right hand side of this particular slide. What barite has? It has got three two-fold symmetries, and you can see that this meets the minimum requirement for its being classified as orthorhombic, as of the orthorhombic family, and also you can easily see that the length of the crystallographic axis in the three directions, namely in this direction, in this direction, and in this direction. These three crystallographic axes, they have got 90 degree angles in between them, but all the axes are of unequal length. So that is the reason why this type of mineral gets classified as an orthorhombic mineral. Okay. Next one up in the order is a crystal system called the hexagonal crystal system, and the name makes it very clear that you are going to have a hexagonal symmetry in this case. That means you are going to have at least one 3 or 6-fold symmetry. Now the example is shown on this particular slide is that of beryl, mineral called beryl. And first of all, let us discuss how the crystallographic axes in this case are going to orient with each other. They are this family requires at least 4 orthogonal crystallographic axes. So, the angle between the major axis, let me consider the example that is given here is that of beryl. So, in this case what you got, one of the axes is going to be like this, and then perpendicular to it will be 6 axes. So, 3 to the center of the 3 faces that you can see in the front, and there will be another 3 axes on the back side. So, the angle, these angles are going to be 90 degree. That is not to say that the angle between the set of crystallographic axes in the horizontal plane are also going to be 90 degree. They are going to be, in this case, inclined to each other at 60 degree angles. Now, this type of crystal could be again open or closed crystals. And we already have considered the example of the mineral beryl. It has got, this particular mineral has got 6 two-fold symmetry and 1 6-fold symmetry. So, if you rotate this mineral about the about the axis which goes from top to bottom, you are going to repeat the pattern 6 times for a 360 degree rotation. So, that gives you a 6-fold symmetry, and for each one of the horizontal axes, crystallographic axes, you have got similar appearance on 180 degree on similar appearance 180 degree apart. So, you have got 6 axes that are going to give you two-fold symmetry. That explains this type of crystals, hexagonal crystals. Let us move on to the next one. Next one, we have got trigonal crystals. Here we have got 4 set of axes, and the four axes, they are going to be orthogonal to each other. Now, what you got here, the symmetry requirement in this case is that you need 1 3-fold symmetry. The form in this case could be again open or closed form, and examples include tourmaline and dolomite. Tourmaline crystal, a schematic of a tourmaline crystal is shown here, and you can see that tourmaline is an open form crystal, and the 3-fold symmetry is pretty obvious by looking at the nature of this crystal. Let me explain this one a little bit more. So, if you consider this axis here which goes from top to bottom, if you rotate the crystal, by 120 degree, then the face, this face, let me label the faces by different colors. So, let us say we begin with the configuration as shown on the slide here, and we turn the crystal 120 degree about the axis marked on the crystal. So, if we turn it 120 degree, then the red faces are going to occupy the face that is occupied previously, by cyan faces, and the cyan face is going to go to the place that was previously occupied by the green faces, and the green face will occupy the position of the red face, and that also give you an identical appearance as compared to the original configuration of this particular crystal. and again you can give it another, you can imagine that the crystal is turned by another 120 degree, again you will be able to see that the symmetry is going to be ensured for that particular rotation as well. So, what you are going to get in this case is 3 different orientations, angular orientation, in which you are going to repeat the pattern, repeat the appearance. So, thereby you have got 3, actually you have got 1 3-fold symmetry in this case. All right. So, the next one of the crystal systems is called the monoclinic crystal system. The name makes it very clear what is meant by the by this type of crystal, by this type of geometry. Mono means one and clinic means inclined. So, here what we have got, one of the axes is going to be skew to the other axis. Symmetry requirement, it really depends on the crystal type that you are considering. So, the essential requirement in this case is that one axis is going to be skew. If that is met, then the symmetry requirement will depend on the individual type of crystal that is being considered. 2 of the examples, gypsum and orthoclase. Both of these crystals is shown on the right of this particular slide. Okay, gypsum for okay, let's move on to the next one. Finally, we have got a triclinic system, crystal system, and this one, the name again is very obvious, the meaning of the name is very obvious. All the axes in this case are going to be skew, and here you won't have any symmetry, there will be no symmetry. The form in this case is going to be open, and example, one of the examples in this case is plagioclase or albite, and a schematic of an albite crystal is shown on the right side of this particular slide. All right. Now, optical properties of a crystal system in the visible spectrum. What are the different types of optical properties that allows us to distinguish one crystal, one type of mineral from another? The first one is transparency. A crystal may be transparent or translucent or opaque. That means it is going to be giving passage to optical signals or light, visible light, without much hindrance. Then you have got a crystal that is transparent. Then secondly, if it is partially blocking the passage of light, then you have got a translucent crystal, or it could be totally opaque, in which it does not allow any light to pass through. Examples are quite you can easily think about some examples. For example, quartz will allow the light to pass without difficulty, whereas if you have got a crystal of galena, that is going to be totally opaque, and it is not going to allow any passage of light through. Now, this opacity will depend on the wavelength as well. That means some of the crystals may be opaque to visible light, but it may not opaque to X-ray. So, this gives you a handy tool of one of the handy tools of distinguishing one mineral from the other. Then some of the crystals, they will be opaque to non-polarized light, whereas if you let through a polarized light oriented in a particular direction, oriented along a particular crystallographic axis, then the light is going to pass through. Example is tourmaline. Tourmaline is going to let through lights polarized through the longer axis, and that is the reason why tourmaline crystals are used in diffraction gratings in optical instruments quite frequently. Then the second one that we are going to consider, optical property that are going to be that are used very frequently in classifying minerals is dispersion and total reflection. A refractive index is a function of wavelength, as you all know, and this gives rise to brilliance. For example of that is diamond. Okay. The other important optical property that allows us to distinguish between different types of crystal families is double refraction, or it is also known as birefringence. What is meant by birefringence is that if you actually allow light to pass through an anisotropic mineral, then light rays are going to split into two rays, and on the other hand, if the ray that is passing through is oriented along a particular it is oriented in a certain preferred direction, that is called a preferred direction, there will be no birefringence, and this special direction is called the optical axis. If you have got isometric crystals, you should remember that there will be no birefringence. Hexagonal and tetragonal crystals have got one optical axis, and orthorhombic, monoclinic and triclinic crystals have got two optical axes, and they are generally skew. This cartoon here actually gives you an example of birefringence, in which an object is placed underneath a calcite crystal, and you can see that that particular object is splitting into two. One of them is appearing here and the other one is appearing here. All right. Now we are going to actually consider another tool that is used to distinguish optical properties of crystals, and that is X-ray diffraction. What is done in this case is X-ray is X-ray is impinged on a sample of powdered crystals, and because of the regular distribution of the atoms in the body of the powdered material, there will be a scattering. Now scattering will be these scattered light is going to interfere with each other constructively or destructively, depending on what is the direction in which the scattered light is scattered X-ray signal is observed, and the pattern of destructive and constructive interference actually is a fingerprint. Actually it is a unique characteristic of a type of mineral, and that allows us to distinguish identify actually one mineral from another. A schematic of an XRD instrument, X-ray diffraction instrument, is shown on this cartoon here, and you can see here what we got is an X-ray source that actually made to impinge on a powdered crystal sample, and then we have got a receiver that we can move actually along this graduated scale, and we can note the intensity of the signal that is coming out of the powdered sample. And what we do actually, we plot the intensity of the received signal as a function of the angle, and what we get in that process is this. So here we plot the angle, and on the vertical scale we have got the intensity of the X-ray signal, and you can see at different angles, depending on what mineral you are looking at, you are going to receive a very intense radiation. For instance, in case of montmorillonite, you have got a radiation, a peak signal appearing at 12 degree of angle. Now sometimes instead of 2 theta you also could plot a d value really, and d converts into theta as shown in that equation there. Okay. So finally we summarize what we discussed in this particular lesson. We looked at crystal symmetry and crystallographic axis. We examined different types of crystal systems. We looked at optical properties of crystals, which allows us to distinguish one mineral from another. Some of these properties are their behavior in visible spectrum. We also considered the principles of X-ray diffraction, and we examined different XRD patterns of minerals. Now actually, by comparing a particular type of mineral with set standard XRD patterns, you could actually identify minerals, as we are going to see in one of the questions that we are going to consider in this lesson. I am going to give you as a part of this lesson. So this is the question set with which we are going to close this presentation. The first question is that what is birefringence, and would you expect a halide crystal to be birefringent? You should explain why you say what you are saying. And the second question, in the second question you have been given an XRD pattern shown on the left of this particular slide, and you are asked to identify one of the constituent minerals of this particular sample. Okay. So with that we are going to close with a note that the answers as usual will be provided in the next session. So until we meet in the next time, bye for now. Thank you very much.